In this segment, we'll talk more about how to find the coefficients of a minimum jerk trajectory. Recall that we can find the minimum jerk trajectory by solving the following minimization problem. By using the Euler-Lagrange equation, we find that a necessary condition for the minimum jerk trajectory is that its sixth derivative must be 0. This leads us to conclude that a minimum jerk trajectory takes the form of a fifth-order polynomial, which has 6 unknown coefficients. Our goal is to find the values of these coefficients. To do this, we define 6 boundary conditions. Let's write out each of these boundary conditions explicitly. The position of the trajectory is given by the function x of t. At time 0, this function evaluates to c0. According to the boundary condition, this must be equal to a. At time big T, this function evaluates to the following expression. According to the boundary condition, this must be equal to b. Note that in this expression, the constant big T is exponentiated to various powers. However, because big T is known, we can evaluate these exponentials explicitly and they become constants. The unknown coefficients are not exponentiated. Therefore, this expression is linear in terms of the coefficients. We can rewrite the position constraint at t equals 0 in matrix form. Here, we see that we are multiplying a 1 by 6 matrix with a 6 by 1 matrix, which will result in a 1 by 1 matrix, or simply a constant. Further, if we carry out the matrix multiplication, C0 will be multiplied by 1, and all the other coefficients will be multiplied by 0. Thus, this matrix expression is equivalent to the constraint C0 equals A. We can similarly represent the position constraint at time big T in matrix form. Again, because big T is known beforehand, the matrix on the left contains only constants. We see that the second matrix term on the left-hand side, which contains our unknown coefficients, is the same as the second matrix term of the left-hand side of the position constraint at t equals 0. Next, we consider the velocity constraints. We can find the function for the trajectory's velocity by differentiating the position function x of t. The conditions at t equals 0 and t equals big T give us the following constraints. As before, we can write the constraints in matrix form. We can write the constraint at t equals 0 in the following way. We can do the same for the constraint at t equals big T. Again, we see that the matrix containing the unknown coefficients remains the same in both these constraints. Finally, we can repeat this process for the acceleration constraints. We can differentiate the velocity function to get the acceleration function. From this, we can write the conditions at t equals 0 and big T. We can then write these constraints in matrix form. As you probably expected, these expressions also contain the same matrix of unknown coefficients we saw earlier. Because all 6 constraints can be written as a 1 by 6 matrix multiplied by the same 6 by 1 matrix, we can combine them into a single matrix expression. Here, each row of the 6 by 6 matrix on the left-hand side, in conjunction with the corresponding row of the 6 by 1 matrix on the right-hand side, represents one of the boundary conditions. Again, because T, A, and B are known beforehand, the only unknown variables appear in the matrix of coefficients. We can now use one of the many techniques to solve for this matrix of unknown coefficients. Let's consider an example. Here, big T equals 1, A equals 0, and B equals 5. We can substitute these values into the expression from the last slide to get the following matrix problem. If we denote the 6 by 6 matrix on the left-hand side as A, and the 6 by 1 matrix on the right-hand side as B, we have a problem in the form AX equals B, where X is the matrix of unknown coefficients. We can find X by inverting A and multiplying it by B. This will give us the following matrix for X, which contains the values of the unknown coefficients in the order that we designated. This means that the minimum jerk trajectory for this problem is x of t equals 30t to the 5th minus 75t to the 4th plus 50t cubed. We can verify that this trajectory does in fact satisfy all boundary conditions. Evaluating the function x of t at 0 and 1 gives us the values 0 and 5 respectively, as we specified in the boundary conditions. We can differentiate x of t to get the velocity function x dot of t. This function is 0 at both 0 and 1. Finally, we can differentiate once more to get the acceleration function. This function is also 0 at both 0 and 1. It is important to notice that when transforming the boundary condition expressions into matrix form, the order in which we place the unknown coefficients matters. We must ensure that all coefficients are matched up with the right constants. For example, in our example, the matrix expression for the position constraint at t equals big T was this. If we reverse the order of the unknown coefficients in the second matrix term on the left-hand side, we must also reverse the order of the terms in the first matrix term. We can change the order of the unknown coefficients in the second matrix term however we want, as long as we make sure the corresponding coefficients in the first matrix term match up. When solving the complete problem, it is important that we order the unknown coefficients in the second matrix term in the same manner for all constraints.